Hi, welcome to engineeringtalks.com. In this video, we'll go through the topic pure bending or symbol bending. We all know that when a beam is subjected to an external load or external force, shear force and bending moments will be set up at all sections of the beam, right? And this beam undergoes certain deformation as a result of this shear force and bending moment. In order to nullify such effects, the material of the beam will offer resistance or stresses against those deformations. So what are bending stresses? So bending stresses are the stresses developed along the length of the beam which is subjected to a constant bending moment and zero shear force or no shear force at all. That is, stresses developed along the length of the beam which is subjected to only a constant bending moment are the bending stresses. And that portion or that length of the beam which is subjected to a constant bending moment only is said to be in pure bending or simple bending. I'll explain this using the shear force and bending moment diagrams, okay? In order to understand what is meant by pure bending or simple bending, let us analyze this beam. Here is a beam which is simply supported at the ends A and B and is overhanging by the same length at each of the supports. So here you can see that it is overhanging by a length of A meters at each of the supports. And due to the external loads acting at the ends C and D, we have reactions RA and RB acting at each of the supports. Now, let us draw the shear force and bending moment diagrams of this beam. In the previous videos on shear force and bending moment diagrams, I have explained how we can draw the shear force and bending moment diagrams for different types of beams. So you can watch those videos in case you have any doubt. If you are analyzing a beam from left to right, all the downward forces will be considered as negative and all the upward forces will be considered as positive. Let us analyze this beam from left to right. So at this end C, we have a force W which is acting in the downward direction. So it will be negative. Therefore, shear force at C will be equal to minus W Newton. And this value of shear force, that is minus W, this remains constant between the points C and A as there are no other forces acting between these points. Now at this point A, we have an upward reaction force and it will be positive. Therefore, at A, shear force will be equal to minus W plus W, which is equal to 0 Newton. Now this value of shear force, that is 0 Newton, remains constant between the points A and B since there are no other forces acting between these two supports. Therefore, the shear force between the points A and B will be equal to 0. At B, we again have an upward reacting force, that is RB, which is equal to W. Therefore, it will be positive. Therefore, at B, we have shear force equal to minus W plus W plus W, which is equal to plus W Newton. And this value, that is plus W Newton, remains constant between the points B and D. Now let us find out the bending moment values along the length of this beam. Since we are analyzing this beam from left to right, all the anti-clockwise moments will be considered as negative and clockwise moments will be considered as positive. So at this end C, we will have bending moment equal to 0. At A, bending moment will be equal to W into A and it will be acting in the counterclockwise direction. So any moment in the counterclockwise or anticlockwise direction will be considered as negative. Therefore, at A, we have bending moment equal to minus W into A, which is equal to minus WA Newton meters. At B, bending moment will be equal to minus W into distance between C and B is A plus L. So minus W into A plus L plus W into L. Why plus? Because the moment at this point B due to the reaction force RA will be in the clockwise direction. So any moment in the clockwise direction will be considered as positive since we are analyzing this beam from left to right. So at B, bending moment will be equal to minus WA minus WL plus WL. So minus WL and plus WL will get cancelled. So what is left is minus WA Newton meters. So from these two values, we can see that the bending moment is constant between the points A and B, right? Now let us find out the value of bending moment at this end D. So bending moment will be equal to minus W into A plus L plus A. That is 2A plus L plus W into L plus A plus W into A. Bending moment at this end D due to the reaction force RA and the reaction force RB will be positive since both the reaction forces RA and RB will create positive moments with respect to D. Now, we have minus 2WA minus WL plus WA plus WL plus WA, which is equal to 0 Newton meter. So, at the points C and D, we have bending moment equal to 0. And at A and at B, we have bending moment equal to minus WA Newton meter. First, let's draw the shear force diagram. For that, we have to draw the baseline. Now, at C, we have shear force equal to minus W Newton. Since it is negative, we'll mark it below the baseline like this. This value remains constant between the points C and E. So, we'll mark it using a straight line like this because this value remains constant between the points C and E. At A, shear force becomes equal to 0. So, from here, it becomes equal to 0. And this value remains constant between A and B. So, between A and B, we have 0 shear force. Now, at B, shear force becomes equal to W Newton. Since it is positive, we'll mark it above the baseline. So, this is plus W Newton. And this value remains constant between the points B and D. Okay. So, this is the shear force diagram for the beam shown. And you can shade these two regions as well and mark it as negative and positive. So, this is C, this is A, this point is B, and this is D. And this is W Newton, this is also W Newton. So, this is the shear force diagram. Now, let's draw the bending moment diagram. So, for that, what do we have to do first? We have to mark the baseline. So, this is the baseline. At C, we have bending moment is equal to 0 Newton meter, and at A, bending moment is equal to minus WA Newton meter. Since it is negative, we'll mark it below the baseline. So, let's mark this variation of bending moment from C to A like this. That is, bending moment varies from 0 at C to minus WA at the point A. Now, this value, that is minus WA, remains constant between the points A and B. So, let's mark that using a straight line like this. Now, this bending moment again decreases back to 0 at this end C. So, let's mark that variation using a straight line like this. So, this is the bending moment diagram, and we can shade this region and mark it as negative. This is C This is A, this is B, this is D. And here it is WA, this is also WA. So this is the bending moment diagram, and this is the shear force diagram for this B. From these two diagrams, it is quite clear that there is no shear force between the points A and B, but the bending moment between these 2 points is constant and its value is equal to minus WA Newton meter. So this means that the beam is subjected to a constant bending moment only between these 2 points. And this condition between A and B is known as pure bending or simple bending. Please do like and share the video and subscribe the channel. Thank you.